Get started. Great. Well, welcome. My name is Wes Hines. I'm the Nuclear Engineering Department head here at the University of Tennessee in Knoxville. Today, we're very lucky to have what I think is going to be a fabulous talk by Dr. Ed Blandford. Ed's the co-founder and chief technology officer at Kairos Power. He's responsible for technology development, experimental testing, modeling and simulation, as well as fuels and materials activities at Kairos. Prior to co-founding Kairos Power, he was at the University of New Mexico, where he was an assistant professor in the Department of Nuclear Engineering. Dr. Blandford was also
working on it. Let me try again.
Hey, Dr. Miller, you're unmuted. Great, thanks. Sorry about that, everyone. Dr. Blandford was also a Stanton Nuclear Security Fellow at the Center for International Security and Cooperation at Stanford University. He also worked several years as a project manager at EPRI, focusing on steam generator thermal hydraulics, material degradation management. He has a Bachelor of Science in Mechanical Engineering from UCLA and both a Master's and PhD in Nuclear Engineering from the University of California, Berkeley. Welcome, Dr. Blandford.
Thank you, Wes. And maybe I should have asked you earlier, but how much time? I think we have the hour, but would you like me to go for, say,
yeah, so usually 45 minutes, and then we'll leave some time for Q&A.
Excellent. All right, great. And so I'll try and check the chat window to see if there are questions as we go, so I can provide context. So thank you for having me, and my apologies for not being able to come on campus. I was really looking forward to seeing old friends and colleagues and meet a number of students as well. But unfortunately, with all of the things, COVID and travel policies and all of that, I wasn't able to make it. So I'm glad we're able to still have the talk, as well as provide a little bit of an overview of Kairos, who we are as a company, our origins, and where we're going. We always start our talks off with our mission statement, and this is central to everything we do at Kairos. And our mission is really to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment. And we believe in order to achieve this mission, we have to prioritize our efforts really on a technology that is both affordable and safe. And I'm excited to talk through where Kairos is as a company, where we're going. But the announcement that we're bringing a low power demonstration reactor to Tennessee is really the first major demonstration. And keeping our eye on this mission is really what keeps us going and getting up in the morning and working hard. Just a quick overview of the talk. I'm going to talk just a couple slides on the background of our technology, what we call FHR, fluoride salt-cooled high temperature reactor, FHR for short. So talk a little bit about the beginning. Then really focus a good chunk of time on who Kairos is as a company, how we do development, why we think we're a little bit different, and how we take our technology from low TRL to high TRL. And then last but not least, talk a little bit about the Hermes demonstration reactor program that we're putting in here in Tennessee. So just a little bit of background. The fluoride salt-cooled high temperature reactor, it's a mouthful, I apologize, so we'll just go with FHR. It's really an amalgamation of a number of different technologies. Many people are familiar with the upper right figure. This comes from the Gen 4 forum, where we bucketed different advanced technologies, non-light water reactor technologies, from the VHTR to the MSR, the SFR, and so on and so forth. And really at the time, this was in the early 2000s. For those of you who know Charles Forsberg, who formerly at Oak Ridge and now at MIT, he likes to think differently about problems and creatively about problems. And he was looking at this and he kind of said, hey, you know, we've got this great fuel from the VHTR, the coolants that really, you know, were popular with the molten salt reactor program. In this case, fluoride salt coolants have some unique attributes. And last but not least, elements of the safety case of an SFR design, low pressure, high temperature, the ability to leverage unique safety systems. Are there opportunities to do sort of these 6 boxes differently? We'll include lead cooled as well into the sodium cooled. So basically fast reactor spectrum technologies. And as a result, there was a thought that maybe we combine the coolant with the high temperature TRISO fuel and the ability to maybe develop a new class of reactors. And so this was a paper that was pretty much what kickstarted a lot of the US development around FHRs. At the time, they were called AHTRs. And really, it's a combination of these different technologies. And so the root of FHRs started in the early 2000s, originally through Oak Ridge, but then really pushed through a number of different university and subsequent Oak Ridge programs funded by DOE. Like many things, there's a lot of research being done both at the national labs and at the universities. And so this is a little bit of an historical walkthrough of the origins of FHR, starting from that early 2000 time period. There was a lot of work to reinvigorate fly work, and a lot of that was actually done at the University of Wisconsin-Madison. They had a lot of experience working with fly predominantly through the fusion program, and this reinterest in looking at fluoride salt coolants for different types of fission applications was really kickstarted at UW. There was a lot of work done through the universities. Some of this was funded through the Department of Energy IRP programs. So the initial IRP that started to look into this technology was a combination of MIT, Berkeley, and Madison in terms of developing sort of some of the early concepts. There was some interest from the Chinese Academies of Science where they were looking at a liquid fueled reactor, which has some overlap with some of the technology development needs for the FHR. And so there was a CRADA put in place between Oak Ridge and the Chinese Academies of Sciences. And so there was a lot of active research that was going on. Around the time of 2015, 2016, there was a recognition that a lot of this was active research. It was good research. It was pushing certain elements of the technology forward, a lot of good universities and national labs. There's a big interest in doing paper reactor design or PowerPoint reactor design. So a lot of conceptual designs were being pushed both at the university level as well as through national labs. And so around this 2015, 2016 time period, there was just a recognition that while this work was great, it wasn't going to lead to a commercialized technology. And in order for it to be successful, it would actually have to leave the university and national lab arena where it was predominantly being developed and pushed and go into the private sector. And that led to the inception of Kairos Power, which was incorporated in 2016. Really at the end of the year, 2016. And I'll talk a little bit about the history of Kairos moving forward. So we're a mission-driven company, as I mentioned, and we're singularly focused on the commercialization of one technology. We're not looking at lots of different types of applications of our technology. So we're really focused on commercial deployment of the FHR. And we believe very strongly that there are opportunities in the United States for deployment. As I mentioned, we were founded in 2016. We have about 210 employees across different sites, and I'll talk about those sites shortly. We're heavily engineering focused, so we're about 90% of our staff is engineering. And I think that number still holds true where we currently stand. We have private funding committed to our engineering design and licensing programs, as well as physical demonstration through both our nuclear and our non-nuclear technology development program. We believe, like a number of our competitors, for us to be competitive, we have to focus on natural gas, not on nuclear that is unfortunately going out and being decommissioned. And so we believe very strongly that we have to be competitive with all sources of generation that utilities are considering across the United States. In terms of locations, we have our headquarters is located in Alameda. We acquired an old naval hangar out on Alameda base, the naval base. If you're familiar with the Mythbusters show, it's a site where a lot of funny things happen. It's a neat space, and we moved in there in about 2017. We also have a location in Albuquerque, New Mexico, which we call KP Southwest. It's where we house what we call our engineering test unit, as well as our larger scale qualification testing. It's also where we've stood up production, development, manufacturing capabilities. And I'll talk a little bit more about what that means in a second here. We recently announced that we've acquired the old K33 site, or parts of that site, out in Oak Ridge, Tennessee, where we're deploying our Hermes test reactor. We have a small footprint there today in Tennessee, but we hope to build up that footprint over time as that project matures. We also have a partnership with Materion, which is a beryllium provider. Their headquarters actually in Ohio, and we have a satellite site there. We're jointly focused on salt production in Elmore, Ohio, at what they call their Pebble plant. And then last but certainly not least, we have a number of licensing staff who are located not too far away from Tennessee, in Charlotte, North Carolina, close proximity to NRC for subsequent licensing engagements. Here's just some quick highlights around Kairos. As I mentioned, we were founded in 2016. We moved into our headquarters in 2017. We kickstarted what we call a rapid lab, which is an area where we work with surrogate fluids, all the way up to nitrate salts, starting with water, where we're able to move quickly and iterate through the design space. In 2018, in October, we kickstarted our pre-application engagement with the NRC. This was crucial in terms of buying down licensing risk around the FHR technology. And I'll talk a little bit later about what that engagement looks like. In February 2020, unfortunately, right around the start of the pandemic, we acquired a site out in Albuquerque, which we call our KP Southwest site, which houses manufacturing and testing capabilities. We signed a collaborative development agreement in March of 2020 with Materion to form our strategic partnership. We started working with Flibe in Alameda in what we call our SALT lab, and we just came up on our 1-year anniversary of safe operations in that lab, working with Flibe proper. Moving forward to December in 2020, we were a fortunate winner of the ARDP program, and we have partners with Idaho National Lab, Oak Ridge National Lab, EPRI, as well as Materion, and we announced our site for the Hermes reactor in Tennessee. We began basically construction on our Pebble development lab. So as I mentioned, we use Pebble fuel for the KP-FHR technology. And so we're developing the capabilities to basically develop our fuel form. In May 2021, we signed a collaborative development agreement with Tennessee Valley Authority. We completed our T facility out in Albuquerque in June of 2021. We initiated geotech, which is very exciting to get out to the site in Tennessee, to go out and do early site characterization work for the Hermes site. And this is a picture on the lower right of them doing some drilling and the site proper. And then last but not least, we're very pleased to announce that we submitted our PSAR for the Hermes reactor. It's a preliminary safety analysis report that was submitted just last month. So we've been very busy. Lots been happening at Kairos, and these are just some of the highlights associated with it. So as I mentioned, really a combination of the high temperature gas reactor technology and the MSR technology. This is a Kairos Pebble on the left-hand side. For many people who may be more familiar with the gas reactor program and Pebble fuel historically, think of Kairos as being golf balls, and think about sort of HTGR and PBMR Pebble sizes as billiard balls. So we're smaller diameter. On the lower left is trace of particles. That's actually a pressed pebble that Kairos has made on the left-hand side. And then we also utilize a high temperature fluoride salt coolant, Flibe. If you can see, I think on the lower right is sort of the historical picture of Flibe that you see when you bring it up on Wikipedia. And this is just a picture of our first Flibe melt in our S lab, showing the Flibe. It's a transparent coolant. It's an excellent coolant for us to be able to work with. And there's a number of reasons why we've down selected to Flibe. And I'll talk a little bit about some of those shortly. This is how do I put it? This is this encapsulates virtually everything we do at Kairos. For those of you who have seen our talks, we show this a lot. We borrowed this actually from a SpaceX presentation, but we believe very strongly for Kairos to be successful, we have to take very long development cycles that have plagued historically the nuclear industry and compress them into shorter cycles. And so What we've observed actually is, if you're familiar with sort of the history of pushes to get advanced reactors going since maybe the 50s and the 60s, what ends up happening with these very long conventional nuclear development cycles is an inner loop emerges within the big loop, which is you get stuck in this planning and designing, and you actually never get to the opportunity to go off and build and test the technology. And so you end up in sort of this inner loop of planning, designing, talking, planning to build, but never getting there. And it's a little bit counterintuitive, but we believe the way to get to the build test for the big loops that you're interested in getting to is actually through a series of iterative smaller loops, where that test experience actually gets incorporated every single step. And so this is key to everything that we do. It's key to our development. It's key to our licensing strategy. It's key to our commercial engagement. Breaking down problems that notoriously have very, very long time cycles into shorter time cycles is key to what we believe is going to be our commercial success strategy. In order to do this, you have to have the capabilities and the know-how to be able to implement small loops quickly. And so, as I mentioned, we have what's called our Rapid Lab and our Salt Lab located in our headquarters in Alameda. We stood up our component testing facility in Albuquerque, where we're able to work with metric tonnage scale of FLIBE. And then last but not least, we have what we're calling our U facility. The U facility, I'll talk a little bit later on. This is a full-scale prototype of the commercial plant, so not of what Hermes is, but actually the commercial plant, and it's the nuclear island. It doesn't exist yet. We have some sites that we're considering for it, but right now the focus is really on the upper three facilities that I mentioned earlier. But we believe this is going to be important for commercial users to be able to get acquainted with the technology, how to operate the physical hardware, how to be able to do remote inspections, to do replacements, all the practical things that go into running a nuclear power plant. We believe the user facility is a place, in addition with, of course, simulator work and other virtual tools that can be utilized to give a customer the confidence to be able to operate the technology. So as I mentioned, we're big on iterative development. We believe hardware is worth 1,000 calculations. So we're very focused on delivering hardware. On the lower right, it shows some of these loops that I was mentioning earlier. I'll talk a little bit more about them in detail. On the lower left, if you look at the lower right picture, we started off with a very small integrated demonstration of what we call our engineering test unit. That's a water-based test. That leads into what we're calling our engineering test unit. This is actually a pretty substantial non-nuclear mechanical demonstration of our Hermes plant. It's of similar comparable scale. It has about 12.5 metric tons of FLIBE, so it's the largest FLIBE test that's ever been done. This is currently an activity that's going on in Albuquerque, and I'll speak a little bit more to it and show some pictures in a second. The next iteration is going from a non-nuclear iteration to what we call our Hermes reactor. This will be in East Tennessee. And then go into, again, a non-nuclear demonstration, which is our U facility, all the way out to what we call our KPX, or our commercial plant. So it's both iterating at scale, iterating between non-nuclear and nuclear. We believe we're able to move faster in a non-nuclear environment to do major de-risking with these high temperature salt systems. And we want to leverage the ability to move quickly where possible. So I'm going to talk a little bit about what we call little loops. So as I mentioned, those sort of 4 big steps that I talked about earlier will be what we might call large loops, if you will. But in order to get to the large loops, you actually have to do iterative smaller loops. So these, I'm just going to walk through a couple quick examples of how we in practice implement this iterative development, both in Alameda and in Albuquerque. So primary salt pumps is a good example. The technology is not off the shelf. It's not readily available for FLIBE applications. There's been a lot of work and a partnership actually with Barbara Nichols to be able to develop this pump. But there were a lot of key questions along the way. And so, while we're very hardware focused, I want to assure you that we are, fervent believers in the value of modeling and simulation where it makes sense. Some of the loops I'm going to talk about are kind of in the context of where doing test demonstrations have been able to help either complement or even replace simulation work where needed. And so there was a lot of design work that went into what we call our primary salt pump, our PSP. And a lot of predictions about both pump curve, vibration. How do you manage thermal management? So how do you go from a 650-degree salt environment all the way up to 110 degrees, for example, in containment, to be able to manage those thermal gradients? And so we have to have the appropriate ability to manage that thermal gradient. And so that becomes a real engineering challenge. And so we were able to build both some water loops and some nitrate salt loops to be able to inform upper head components, how we actually manage these thermal gradients appropriately, as well as actually work and partner with Oak Ridge National Lab on some innovative manufacturing processes. So the impeller on the lower right, that's an additively manufactured impeller. We'll be utilizing that impeller in our engineering test unit. There was a lot of work done looking at the quality around the build, ensuring that the integrity of the build was appropriate for the application. But this is an example where we're able to incorporate different elements of both manufacturing and testing to be able to improve and optimize the design before it ultimately gets demonstrated in the engineering test unit. In addition, control element drives. This is a unique technology. It's a technology, again, that's not off the shelf. No one has ever built an FHR. And so there are challenges about taking what might work for an SFR or what might work for an HTGR and what really needs to be done for this type of environment. And so there were some key questions, similar challenges, because these are all components that sit on the upper head of the reactor vessel, where elements of conventional drive mechanisms really didn't apply to our environment. And so we've done a number of development tests, really testing out some of these mechanisms, ensuring that their fit and function perform well in this high temperature salt environment. We've also been able to look into opportunities around more conventional manufacturing to be able to improve the sort of the design for manufacturability of these different components and then demonstrate them. And so in all of these different applications I'm walking through, there was a baseline simulation effort to kind of inform the performance of these types of components. But it's really bringing it into the lab, developing the hardware and demonstrating that it ultimately works that gives us that greater confidence. Just check really quickly, nothing in the chat. Not everything we do is just around development. We also have validation testing needs. And so one of the key questions in the downcomer region for our vessel, it's a high priority phenomena for our reactor safety case, especially as we're looking at in-vessel natural circulation, if we're looking at a range of different transients such as loss of force cooling transients. One of the unique features of the salts at 650 degrees C, there was a lot of work historically done showing that you can actually use simulant fluids to preserve some of the key non-dimensional parameters. Ones that are important here are around forced circulation, but the ability to use lower temperature surrogates to get high quality validation data is really unique. The ability to get high quality validation data in a salt environment, just like the ability to get high quality validation data in an LWR environment, is really challenging. And the ability to preserve similitude for a single phase coolant and the ability to get good quality validation data allows us to build confidence in our tools. And so we were able to do this test. It's actually extremely tall. I'm not sure the picture does it justice. It's about 12 to 15 feet tall. Shows some nice tests that we have done using Dowtherm to validate CFD simulations of the downcomer region. And so one of our strategies around IET and SET is the ability to leverage these simulants to be able to build up a predictive accuracy capability with our evaluation models used for licensing. This is key. It's central to our development, and it's a really important aspect of our safety case. Last but not least, as I mentioned, sort of our first big, well, what I call big, but it's actually relatively small demonstration of sort of an integrated test is our engineering test unit demonstration experiment, lovingly called ETUDE. This is, if you look at the engineering test unit, which I mentioned earlier, which is a larger scale integrated test, it's going to be important to be able to to be able to work at a smaller scale. In this case, we're able to use water to preserve some of the key phenomenology. So at about 40% length scale, we're able to look at some of the hydrodynamics associated with the engineering test unit. This is basically the etude test. It's here in Alameda. And it's a nice test that gives us the ability to look into some of the key performance features of our engineering test unit. We're able to look at both some of the mechanical features as well as fill drain operations. And it's a practical tool for operators, for ETU, to be able to get some runtime with the physical demonstration. These little loops lead to big loop integrated demonstrations. And some examples, and again, this is just a re-showing of those loops. So it shows the engineering test unit going to the Hermes reactor and our U facility ultimately leading to the KPX. This shows this progression in, I guess, a little bit more of a coherent snake chart. Again, non-nuclear to nuclear to non-nuclear to nuclear. Switching gears here, talking about sort of larger scale demonstrations. This is the engineering test unit as it's compared to our first commercial unit, which is the KPX. What is our engineering test unit? It's a non-nuclear, unenriched, fly-wetted, and isothermal test. So it effectively uses all of the same mechanical features that you would see in our Hermes technology, but it's obviously non-nuclear. And so it's a full-scale version of Hermes, and it's proportional to the KPX demonstration. Why? Well, we're very interested in ensuring competitive cost through vertical integration. This is a very important aspect of the Kairos development. Also, we want to be able to flex our supply chain early in the development, and that's really key. In addition, it allows us to be able to demonstrate our design and test elements of our program, and the ability to do sort of how can we do this quicker through these iterative developments. The ETU is really a culmination of a number of those smaller, earlier loops. And last but not least, it also allows us to accelerate some of the base of our large-scale FLIBE operations. So as I mentioned, this is 12.5 metric tons of FLIBE. And this is the first time anyone has done a test of this scale. So it allows us to build that operational case and that ability. Shifting gears here a little bit, I want to talk a little bit about the T facility annex. This is in Albuquerque. This is where it houses the engineering test unit. On the left, it shows the 40,000 square foot high bay. We are populating this annex with both the engineering test unit as well as qualification testing. The picture in the middle shows the annex from a distance. It's a tall building. It's got about 65-foot height associated with it, and that's due to the fact that the engineering test unit has to support the components on the upper head, and so we need that high height. And in the lower right, we were fortunate a few months ago to show the Secretary of Energy around and talk a little bit about what our program is doing. Just some pictures for scale. This is actually half of the ETU vessel, so this is a slightly older picture, and it shows the vessel on its side. The support plate or support structure is on the lower right, but this is about half the height. For scale, ETU is not the exact same technology as what we would see for Hermes, but to approximate scale, it gives you at least a little bit of idea about what the vessel for Hermes would look like, and it's about half. That's half the size of the vessel because it's on its side, and they're actually welding the upper part of the shell here shortly. We're expecting to get the vessel on site in Albuquerque on November 1st. So coming up very soon. This is one of our first big vessel lifts that we've done out in Albuquerque. In addition, we believe very strongly in standing up manufacturing capabilities where existing suppliers do not exist. And so we've invested a fair amount of time and effort into graphite block manufacturing at KP Southwest. And these are some non-proprietary pictures of both the capability as well as some of the blocks and where they start before they actually go into becoming part of the reflector structure within the ETU. And I think, let's see if this video works. It just shows, for those of you who have seen graphite machining being done in the past, it's a very, very messy process. If you look at the picture in the lower left, A lot of the HVAC supply that you see on the upper part of the mill there is really a dust collector system that's capable of removing dust in situ while you're doing the machining. So this is a unique capability that Kairos is investing in, and it's really part of our DNA in terms of being able to bring the manufacturing in-house. Just some more snapshots showing the primary salt pump. This shows the shaft and bearing column assembly, as well as some of the pump shaft tests that were being done. Our partners, we worked extensively with both Oak Ridge and Barber-Nichols. Here's some other pictures of the primary heat transport system. This shows some of the piping systems. These are 8-inch diameter stainless steel pipes, so quite large pipe by which the fluoride salt flibe is circulating through for the engineering test unit. Our piping system is designed to meet B31.3, and so we've got some skilled welders here on site that are actually doing a fair amount of the welding to assemble the PHTS. So the final assembly is actually shown in the lower middle picture, showing the PHTS system in the pieces and parts. And if you look at the top of that bottom middle picture, you see where the vessel is to be housed, and that shows approximately what the geometry of that piping looks when it's laid out. Actually, our first big vessel lift was the argon system for our cover gas and vacuum system, and this just shows the start of that CGVS system actually coming together adjacent to the annex. So a lot of exciting hardware builds actually going on in Albuquerque. One of the neat things, and I'll talk a little bit later about this, is we found great success in hiring recent grads. You need to have a combination of experience as well as a combination of a lot of enthusiastic, mechanically inclined recent grads. And there's a ton of opportunities. A lot of the activities that I just showed earlier, a number of them, in some cases were actually led, but a number of them were actually driven by recent grads, being put into a high-paced environment to be able to take ideation, simple ideas, starting off with early development, and really run them through paces to get into larger scale demonstrations. So we have a fair amount of experience as well on staff, but we have a large number of recent grads and actually a number of grads who come to us from the University of Tennessee as well. It's important that we maintain a quality EH&S program. Working with FLIBE is serious business. Working with the beryllium bearing salt presents its own unique sets of hazards and challenges. We have done, I think, a great job so far working with FLIBE. We're limited in the quantities that we can work with here in Alameda. And we're going to a larger scale where we're going to the engineering test unit where we're working with metric ton scale, and our EH&S program has to scale appropriately. I apologize, one quick second. Yeah. Hey, boss, hang on. Can I talk to you in 5 minutes? I'm giving it time. Thank you. So our EH&S program is a big part of who we're doing right now. It's how we ensure we can work responsibly with salt, and we're very excited to be able to have the record that we have. And we spent a lot of time partnering with the Materion company, which is located in Ohio, as I mentioned, in part of our strategic partnership. They have been central in terms of translating very strong lessons learned from their operations, working with both beryllium fluoride and beryllium in general, and they've been an excellent partner. And so these are just some examples of the type of PPE and some of the training activities that we do out here in Alameda. And I believe last but not least, this just shows the control room, as well as our operations support room in Alameda. We've spent a lot of time incorporating a lot of the lessons learned from historical operations, both from the nuclear side. Our site director at KP Southwest comes to us actually from SpaceX, who has a lot of experience in control rooms for shuttle launches as well, or for space launch. And so really that combination of non-nuclear and nuclear operational background, bringing that into a new environment, operating a large-scale FLIBE system, we believe has given us a great opportunity to bring a lot of best practices from different industries as well as what is needed for a non-power test reactor. Last but not least, this is just a picture of our Pebble development lab. We need 30 to 35,000 pebbles for the engineering test unit. We are we are pressing all of those pebbles in KP Southwest in our Albuquerque site. We've pressed our first pebble in July, and we're about 15% of the way through, and we're moving very quickly through pebble pressing. And this just shows a couple pictures of those formed pebbles. I'm going to transition here, actually do a little bit of a time check. It seems like I've got about 5 minutes left, and then we can hopefully open it up to a broader discussion. The Hermes low power demonstration reactor. What is the low power demonstration reactor? Well, it's a reactor that we hope that will prove Kairos's ability to deliver low cost nuclear heat. Some of the elements or some of the sort of overarching objectives of Hermes actually build off of the engineering test unit. So we want to be able to establish a competitive cost. So we have a very aggressive overnight capital cost target for Hermes. We believe that's important. Our supply chain, we believe it's critical. So our supply chain for engineering test unit is predominantly focused on non-nuclear today. Hermes is obviously a nuclear facility. It's a nuclear reactor. It's going to have those types of specialized components. And so this is a key part of why we're standing up Hermes. Again, to kind of extend that design test paradigm, to be able to bring it to a nuclear demonstration, as well as the licensing approach. It's important to get early buy-in from the NRC in terms of some of the pre-application work we've done, and we believe Hermes is now an opportunity to go through the Part 50 process to actually provide licensing certainty for the KPFHR. So we're licensing this as a non-power reactor pursuant to a new Reg 1537 type approach. However, it gives us early engagement with the regulator that we believe will translate later on to the commercial demonstration. And then last but not least, similar to ATU, it provides a very strong operational basis, but really from a nuclear operations side, if that makes sense. Moving here a little bit along, we're very happy to be recipients of an ARDP award. It's a cost share partnership between DOE and the industry. The total award value over the next 7 years is about $629 million. And so we're very glad to partner with both DOE as well as a number of labs in the form of Oak Ridge National Lab and INL, EPRI, as well as our strategic partnership with Materion. We believe it's essential to work with these entities to be able to deploy Hermes. As I mentioned, our licensing strategy is absolutely essential. We believe very strongly in order to achieve cost certainty for our commercial technology, it's got to be a combination of technology certainty, will it work? Licensing certainty, can it be licensed? Supply chain certainty, is there an existing supply chain? And last but not least, construction certainty. So we've been heavily engaged in a number of licensing engagements. We've submitted a number of topical reports in key areas, ranging from our quality assurance program to strategies around how we design and build our integral effects testing, out to sort of salt chemistry and beyond. And so, as I mentioned, we're very excited to have submitted our PSAR, which was submitted in September of 2021. So last month, this was a huge accomplishment for the team, and our licensing team did an excellent job in terms of getting that deliverable through the finish line and getting it submitted. We know there's a lot of work that goes into supporting follow-on questions around the PSAR, as well as what's going to be needed to submit our final safety analysis report, which will ultimately be needed for the Hermes reactor. And then just a little bit here on the real estate deal. We've acquired the former K33 gaseous diffusion plant site, not too far away from UT Knoxville. Hermes will achieve criticality in 2026. This is obviously out in Oak Ridge. And we're just excited about the ability to come to Tennessee. We've had a great experience in New Mexico, working in Albuquerque and working with the local community. And we've had just an excellent experience so far working with a number of different leaders in the nearby both Oak Ridge as well as Knoxville region. And we're just excited to come to Tennessee. We made a commitment in terms of our total capital investment as well as job creations. I'll just note that we've exceeded that number for what we committed to New Mexico. So I think we have a good track in terms of performance. And we're just really excited to come out and to start the Hermes project. I think that's one of my last slides. So just a quick plug. We're hiring, we're actively hiring. We believe very strongly that for Kairos to be successful, we need to be able to hire recent grads. That means undergrads, that means grad students, that means postdocs even. And we've even had professors come take sabbaticals and get some great sort of mutually synergistic experiences working at a place like Kairos. So we're very interested. If you're interested, we've got a number of balls that have come from UTK. I think a few of them may be on the line. Our director of licensing comes from the University of Tennessee. We have engineers both in modeling and simulation and safety analysis. And as I mentioned, our footprint, physical footprint right now in Tennessee is relatively small as we're starting to get some of the site characterization work out of the way. But we're going to start to build up that footprint and that capability here shortly. And so we're excited to bring in great candidates. And please, if you have any interest in roles, either email myself in the lower right, as well as recruiting@kairospower.com. So I think that's my last slide. This is a video that shows one of our tests, but I think I'll go ahead and I think I'll end there. So Wes, I'll hand it back over to you.
Okay, great. Thanks so much. I'll go ahead and open it up for questions. Here's one on chat says, do you have a fuel supplier yet, or are you planning to make your own TRISO, etc.? Got that.
That's a good question, and that is certainly business proprietary. So I won't be able to directly answer that. But the obvious things you need to fuel Hermes is you need high assay LEU, you need TRISO particles, and then you need your pebble fuel form. We are working on all three of those problems. There are some suppliers out there and there are some opportunities out there. And so we're still evaluating those different options, but we're committed to getting fuel to Hermes. Hermes without fuel is not going to be a great reactor. And so we need to have both. So I can't fully answer that right now.
Okay. Let me ask you, I see a lot of steel and, coming together. How has supply chain and prices affected you? I just, just looking at some things we're doing here, just to get steel prices have gone up, 30%, 40%. I'm sure that has to be frustrating when you put together a budget a year ago and a year later, some of your costs have just really skyrocketed. Have you seen that, I guess?
Absolutely. 100%. While maybe someone will accuse me of being an optimist here, I'll try to take that question maybe a slightly different direction. Everything that we're doing right now with the engineering test unit is really a precursor for what we need to be able to do downstream for the nuclear build. While the pandemic has been a major pain and been a major challenge, it's also been a good litmus test for what can happen when you don't have complete control over a number of different aspects of your project. So our ability to bring in suppliers, our ability to source material. Our structural material is dominantly 316H. One would think 316H is pretty readily available. It's not. It's actually very challenging to source and get equipment that falls into 316H specifications. So in a number of areas, we've made some decisions to actually stand up certain manufacturing capabilities because we can't be overly reliant on external suppliers. That's part of the vertical integration opportunity. It's part of the challenge, but it's also part of the opportunity, is that if you have the appropriate product forms and you've got the appropriate manufacturing capability and the right experience, some of these challenges that we're seeing right now with ETU are being incorporated into lessons learned. And so if we got our procurement team on this call right now, there would be a lot of fun conversations about some of the sourcing challenges that we've actually had. We've had to be creative. But out of that, I think it's been a good litmus test for some of the challenges that you don't see in a conventional non-nuclear build that you would see in a nuclear build. So while, knock on wood, we hope when we're building Hermes, there's not a pandemic and we're not in this environment still, there's going to be other headaches, there's going to be other hurdles that are going to come up. And we believe actually the opportunities that have been afforded us from some of these challenges and doing the engineering test unit are actually kind of good practice go around for the types of challenges we're going to see later on. But to directly answer your question, the cost of steel has gone way up. The ability to procure 316H in a variety of different forms has been a challenge for us and for our procurement team. And it's also kind of one of the examples I mentioned earlier about why we're doing ETU is around the ability to do the design build quickly. It's actually gone back to our engineers in the way that they do designs of systems to understand sort of the appropriate lead times in getting the right product forms that are needed for those pieces and parts that make up what they're actually designing. So it's actually had a very positive feedback loop, even though it's been a big pain in the you-know-what in a variety of different areas.
So there's another question here, again, on the business side. It says, do you find it difficult to find venture capital for nuclear related projects, especially in very early stages like you are?
It's interesting. So we're not in a place where we're actively looking for funding right now, but there actually is a lot of private capital out there that's interested in trying to push clean tech in the right direction. I think there's a number of investors that recognize there are challenges in some of the current popular solutions. And many folks are also interested in how they can actually impact nuclear. I think it's interesting. One of the things that I've observed in engaging with some of these types of folks is there are differing opinions on what are the different challenges that nuclear is facing. Some are very wedded to challenges around the fuel cycle. Some are very wedded to waste reduction, or back-end waste reduction. There's different sort of flavors of appetite for different parts of the problem, but I think there is a general interest. Right now, that's less of an issue for Kairos right now, but we are seeing sort of an increase in private funding going into that area and trying to move the bar. But they are looking for successes. And so I think it's incumbent on the advanced reactor community to actually show some of these successes to be successful.
Okay, the next one says, can you comment on Kairos material selection philosophy and reconciling the drive to innovate with regulatory hurdles and industrial inertia in the adoption of improved materials?
That's a great question. So there's, and I'll try to get myself to not get into trouble here. There are code requirements for your material down selection. And so that drives some of your upfront decision making. The reality is we believe strongly that 316H, which is the structural material of choice for Kairos beyond our ceramic materials, is key and central to our safety case. Having said that, if you look at the history of nuclear materials in general, the industry has always innovated. And so my background in the LWR space was around steam generators. The second Inconel 600 millinneal tubing came out, they discovered there were challenges. There were degradation issues around stress corrosion cracking. We moved to more mature Inconel 690, and there's always this ability to innovate and ensure that we're evolving. And that's also a partnership that you do with chemistry, right? So it's not just solely a materials decision. It's also one that, in the case of light water reactors, you're worried about water chemistry. For us, salt chemistry is an important partner in the evolution of material degradation. So it's difficult. We want to move quickly. We want to iterate fast, but at the end of the day, you have to pick a material down selection. You've got to ensure you've got the appropriate supply chain, and you have to build your technology to ensure that it can go into service. But I will say, we do believe part of our safety strategy, if you will, is by reducing the footprint of what we consider to be safety related across the plant. It does allow us to do maybe more routine replacements of components that fall outside of that sort of that nucleus, if you will, of safety-related componentry, and the ability to leverage evolutions in material improvements and the ability to bring those materials in. And that's not too radical of an idea. We do that with steam generator replacements, and it happens all the time in other components, but it moves slower than you would like in other industries, if that makes sense.
So we'll hop back up to the top where Dr. Worth had a question about the licensing of Hermes. Is that licensed by NRC, and really what's their perspective on the fuel in Hermes?
Sure. So yes, it's licensed by the NRC. I'm not going to speak on what their perspective on the fuel is with respect to Kairos. That's their perspective. We have submitted a number of topical reports around fuel performance and fuel qualification. To my knowledge, actually, some of the SERs have actually been released for those topical reports. So I believe that we are making good headway in our engagement with the staff, but I would let them provide their perspective on our fuel as opposed to me opining, if that makes sense. Sorry, Brian.
Okay, we have
Sounds
another
good. Thanks,
question.
Ed.
Yeah, so it says, can you comment on what the culture feels like at advanced reactor vendor like Kairos during these exciting times? Does it feel like a startup culture, different than existing nuclear industry? How did the company celebrate the submission of the PSAR for Hermes? And congratulations.
That's a great question. We're a mission-driven company. We believe very strongly that we are in for a marathon, not for a sprint. While that sounds nice, I'll just remind folks, marathons are not easy. And the reality is we believe very strongly in work-life balance, but we also want committed staff on site. And so we believe we provide an opportunity for people that believe very strongly in what nuclear can provide. Our culture, we spend actually a lot of time on our culture work. We have desired culture characteristics. We believe very strongly that if your attitude is just what we used to do in nuclear is going to get us to the next innovation or the next thing, and we just need to make marginal improvements, you're not going to be a good fit at Kairos. It's important to leverage both the history and sort of the importance of sort of the regulations that surround our technology, but also come into it with a very open mind about what other industries are doing. They are innovating very, very quickly. They're doing things very fast. Why are we not doing them as quickly? And why are we stuck in these long development cycles? So we're looking for a healthy combination of expertise and people with good backgrounds in certain nuclear types of problems. But we're heavily interested in non-nuclear engineers as well, which I know is sacrilegious to give to a nuclear engineering department, but it's true. We look for a lot of mechanical engineers, chemical engineers, people with civil backgrounds. We're constantly looking for different types of engineers that want to get their hands dirty and want to be able to engage in real hardware and deploying real things. And I think that's, in my mind, those are the types of recent grads that we're looking for. There's a lot on the table. So every time we get a big win, like a PSAR submittal, it's important that we sit down and we celebrate those wins. Unfortunately, in a COVID environment, it makes it a little bit tougher than we would like. But I think culture is actually one of the key aspects or elements of Kairos and what differentiates us. We require people to work hard, but we're action-oriented, we're direct and honest. These are some of the cultural characteristics that really underpin the types of people and the types of the caliber of the types of hires that we're looking for. So it's a fun place, it's dynamic. I'd be lying if I said it wasn't a lot of work, but grad school's a lot of work, and it's extremely fulfilling. And it's like no other place that I've ever had the good luck to go work at. It's very mission driven, and it's a unique environment to come into, especially for someone coming out of a university or an early stage career position.
So I have a question about fuel. I've spoken to leadership at NNSA, and they would love to have a fuel that when it comes out of the reactor, there's no proliferation risk to it. It's hard to separate. You can't get the plutonium out of it and make a device, a weapon. How do you think TRISO fits into that scheme?
That's a good question. I'll again try to keep myself out of trouble and maybe just give my own personal opinion here. We do have our nuclear material security manager who we've recently hired. He comes to us from Y12 and he's not too far away from where you guys are. So maybe I'll pass the buck over to him and have him come and talk to the department in the not so distant future. But my understanding and my belief is the proliferation resistance around fuel really starts with both administrative and engineering control. So having a healthy MC&A program, ensuring that you're tracking and monitoring your fuel. There's a lot of synergies between the safeguardability of fuel and the safety and security of that fuel. So you want to keep track of your fuel for a variety of different reasons. Safeguards is just one of those elements. We're committed to standing up a healthy MC&A program in the event of a theft or a diversion, which is obviously very low probability in our minds. There are challenges in reprocessing TRISO fuel that are unique to TRISO vis-a-vis LWR fuel. Like anything, I think this is possible. And then you start going down a long sort of litany of questions around state actors and all of this great stuff about what are the capabilities to go off and do that. I won't get into that. That's not my area of expertise, but I think inherently there are increased features associated with the fuel that make it more safeguardable or less of a concern from a proliferation resistance standpoint. But there's a lot of complexity surrounding that question, if that makes sense.
Okay. I've just heard, people say that is the TRISO fuel proliferation wise would present much less risk. I just wanted to hear your thoughts.
That is correct. But like anything, you if you put enough time, energy, and money in engineering, but absolutely, TRISO is a lower proliferation risk, I would say, than LWR.
Yeah. And I think they're always looking at, how easily could you disguise it? Maybe the reprocessing, the transformation that would have to occur for TRISO would be much more difficult to disguise, whether it's energy usage or space necessary than maybe, our current fuel forms.
Got it.
Yeah, I mean, that was just what I've kind of heard. Okay. Does anybody have any other questions before we let Dr. Blandford get on with his day? Well, we only had maybe 2 minutes left anyway. So I'd just like to thank you for taking the time to talk to us. I think it's really exciting for me. I've seen some presentations in the past. They've probably been early COVID or pre-COVID, and the slides and to see what's actually been built and what's being tested is really fantastic compared to what we were able to see a year and a half ago or 2 years ago. So congratulations to you and to Kairos, and best luck in the future. And we're looking forward to having a new reactor here in East Tennessee and having you come out and visit us sometime. So thank you very much.
Yeah, I love to, and thank you for the opportunity. It's great to see a number of familiar faces. And like I said, if you've got interest, we've got internships. I'm going to keep plugging it. So send us
Great.
And thanks for the opportunity, Wes.
Okay. Nick, I see you joined us.
Thank you.
Absolutely.
Okay. Take care. Have a great day.